Welcome to Material Science to Empower Quantum Information Technologies. I'm Rick Muller, and two of the co-organizers with me of a session at the Spring 2018 Materials Research Society symposium by the same title are here with me. And so we're interested in this symposium in exploring quantum materials and understanding what exactly people mean when they talk about quantum materials. And one of the curious aspects of this is that people often mean two very different things. One group of people means material science investigations to understand and improve devices for quantum information technology. So things like qubits for quantum computing applications. Another group of people, when they say quantum materials, means exploring novel applications of topological or other quantum properties to material science. And so two of my co-organizers, Chris Richardson and John Gamble, both kind of represent two of those, each of those groups. And so, Chris, could you say something about material science research to improve quantum bits and other quantum devices?
Sure, I can, Rick. Happy to be here. I've had this conversation quite a bit with numerous researchers throughout the country when we talk about quantum materials or materials for quantum applications. My particular research and interest is taking conventional material science skills and techniques. I do material synthesis using molecular beam epitaxy, but I also do device fabrication. And there we're looking at how we can take our conventional tools, materials characterization, apply them to these really interesting and hard problems in quantum information to improve the metrics of performance, whether it's superconductor loss at gigahertz frequencies or charge trapping at dielectric interfaces. But there's just a whole host of problems that are at much different scale than conventional electronic and optoelectronic applications.
And John, could you say something about topological materials and how Microsoft is using them to make other types of quantum devices?
Sure, yeah, thanks, Rick. So at Microsoft, we're interested in pursuing this concept called a topological qubit. And so basically the idea behind that is to develop a material system where we can store quantum information in a topologically protected, non-trivial state. And so in particular, we're dealing with one-dimensional nanowires currently, and storing the qubit in something called the Majorana fermion. So our approach, though, is kind of through a materials engineering point of view. So really what we're trying to do is take several topologically trivial materials, so like a trivial superconductor like aluminum and a trivial semiconductor like indium arsenide, put them together using material science know-how in a way that develops a topologically non-trivial system that then is useful for this type of topological qubit encoding. So it's really taking simple building blocks that we can really understand well from a material science point of view and putting them together in order to get a really complicated system that then starts to exhibit these exotic properties that maybe don't exist in any natural system that's not been engineered.
So maybe a question for both of you. So it seems like there are a couple of intersections between the two areas. One of them is that both of those areas have materials defects in them that limit their performance. And the other in them is that what you both talked about was on quantum information. So maybe I'll ask Chris first, what you see as the kind of research frontiers, the kind of open research questions for how to improve whichever quantum devices you feel like you'd like to talk about. Superconducting and semiconducting are the two that you mentioned so far. What are the open research questions and what needs to be learned in the area?
So I tend to think of it more generally in terms of qubit technologies and what the material science applications that I have. I'm not a quantum physicist. I'm a trained material scientist. I am definitely very interested in quantum information devices. But what really intrigues me is the thought that the concept of making a quantum state and having it be a storage area for information. So actually creating a qubit, having that qubit last a long time, and being able to do manipulations with it. There's a natural thought to think that first you have to make a qubit, but then it has to keep that information for that long time. That's an open quantum system. And so my interest really come from how those loss mechanisms, how this qubit, where the theorists think of it as a perfect entity, can lose its coherency, can lose its energy, and that's all through the environment and through the materials. And so that's the part that engineering and trying to figure out that I'm really focused on. And most of my effort has been on superconductors. I mentioned loss a little earlier, but there are many different things that can come into loss, whether they're two-level systems at surfaces or in amorphous materials. There are quasi-particles or unbound Cooper pairs that can come through and create loss that can be either enhanced or perhaps suppressed if the materials are engineered correctly. And so if I had to summarize it, I would say not necessarily in terms of inventing a qubit technology, but in terms of making qubits better through materials engineering.
And so what do the research questions in that field look like? Are you trying to do structural analysis of the superconducting devices? Are you trying to find improved methods of fabricating devices? And I guess, finally, is there hope that we can substantially improve, let's say, the superconducting qubits that we see out of companies like Google or IBM?
So in terms of my particular interests in superconductors, I'm interested in how the structure goes together. So I've spent a fair amount of time looking at aluminum, which is a conventional superconductor, but its performance in the qubit is limited by the defects. Mostly importantly, it's a thin film of aluminum on a substrate. And we've done a lot of work on how to incorporate aluminum onto a silicon substrate without having any sort of additional intermixing and understanding the structure very well, with the idea that if we understand where every single atom is on both sides of that interface, whether it's aluminum or silicon, can we minimize intermixing? Can we understand where the impurities are? But also to support future possibilities of materials simulation, if we can actually visualize where all the atoms are in a very ordered interface, can we then go back and do calculations to try to understand the fundamental microscopic origins of a loss mechanism, such as a two-level system that might be associated with a dangling bond of aluminum or silicon? I've also looked at trying to make new materials. Aluminum is rather conventional. Titanium nitride has gotten some interest as being a very possible future material. And so I've spent, or I am spending my research efforts now in figuring out how to make high-quality titanium nitride using molecular beam epitaxy, combining some of the semiconductor skills that have been learned in the 3.5 community and applying them to a superconducting material system. And then the questions are all the same. What's the structure? Where are the impurities happening? And what sort of impurities and defects actually couple into the superconducting behavior? Because superconductors are very different than semiconductors in terms of their performance and loss characteristics.
And do you see these additional materials choices that you're talking about promising to substantially improve the performance of superconducting qubits that we see in the literature today?
Yes. So there are issues in terms of integration and incorporation into circuits, but in my own lab, comparing loss mechanisms using a coplanar superconducting waveguide resonator, we worked very hard to get aluminum up to a high quality factor of around 1 million. And our first time out of titanium nitride, we're doing about 2 times better than the aluminum that we see. And so there are inherent differences that we don't understand yet in terms of where these loss mechanisms are happening. It's also very challenging because the energy scales in superconductors is on the order of 5 gigahertz. That's on the micro EV scale, whereas most of the engineering that's been done for electronic and optoelectronic and all the simulation tools that we have are really more geared towards things that are much higher than that in energies. And so it's a whole new energy scale where spectroscopy can catch up. Simulation needs to beat down the achievable resolutions. And it's also very challenging from a characterization and atomistic perspective to see where each individual order and disorder pair or an impurity can bond, because it's very bond specific.
Thanks, Chris. So John, can you tell us a little bit about topological properties and why you would want to build a qubit around topological properties, and kind of what's different about these topological qubits from the kind of qubits that Chris just told us about?
Sure, yeah. So the name of the game in quantum computing, of course, is that you want to have low error rates and robust qubits, despite being able to control them reliably, right? However, the environment by which you are also acting on the qubit, right? You are the environment from the qubit's perspective. Whenever you do quantum gates on the qubit, you are interacting with it to some degree. So the qubit is necessarily vulnerable to environmental fluctuations and perturbations, like what Chris was just talking about. So in conventional qubits, what one typically does is you pile up a lot of physical qubits in order to build in some non-local degrees of freedom so that the quantum information isn't scrambled by small local perturbations in the environment. And this is in essence, so if you heard of the surface code, for instance, this is in essence trying to build in topological protection to conventional qubits. So what we're doing is we're exploiting the fact that if you engineer specific types of topological materials, your physical qubit, so the thing that you are implementing physically in your device, inherits some of the topological protection that's inherent in the topological material that you're developing. So in essence, the qubit is spread out over a large amount of space, and you need to do fairly severe environmental damage in order to scramble that quantum information. So, by no means are we saying that you can stop doing error correction after you have topological qubits, but what that means is that you have a great deal of kind of error correction like protection built in at the physical level, just because the quantum information is stored in a way that is not easily scrambled by a local disorder. So that's kind of the hand-waving explanation.
So can you tell me, so when we look at superconducting qubits, we know people are actually producing qubits, they're measuring qubits. With the topological qubits, we haven't realized them in the same way. And since this is a material science society, I was wondering if you could say something about the materials challenges that need to be addressed in order to realize topological materials or topological qubits.
Oh, yeah.
Where an everyday material scientist can perhaps make an impact in that area.
Yeah, absolutely. And so, I think this is super appropriate for MRS because it turns out that the roadblocks that we're experiencing right now in terms of observing and implementing a topological qubit are mostly materials. So if you think about, let me go through the ingredients that are required to make one of these topological qubits. So you need a semiconductor with strong spin orbit coupling, transparently connected to an S-wave superconductor. So aluminum is a good example of an S-wave superconductor. So this is similar to the aluminum that Chris was just talking about. But we need to engineer this pristine barrier between aluminum, a superconductor, and usually a 3-5 semiconductor that has strong spin-orbit coupling, like indium arsenide or indium antimonide. And only very recently have people been able to do this reliably. So epitaxially deposit aluminum on a semiconductor and get reliable, good, transparent contact. In addition, you have to find ways to shape the aluminum, so to etch or selectively deposit the aluminum. You need to find ways to selectively grow networks of nanowires reliably and preferably as pristine single crystals. You also need to think about how to manipulate these things reliably, which means that you need gate oxides and you need electrodes that go down with minimal defects that aren't going to cause problems when you try to tune up these devices. So in practice, when you go and you try to tune up these devices, and the problem is really getting it to the point where the material behaves as a topologically non-trivial material in the first place, because of all these imperfections in the fabrication and materials defects and so forth. And so understanding how these complicated devices all go together and how the oxide interplays with the aluminum and the aluminum interplays with the semiconductor and the gate electrodes interplay with all of those is really critical to understanding the behavior of these devices and learning how to make them more reliable and better.
Thanks, John. Okay, to wrap things up, I wanted to ask each of you one final question. And that's just, either answer with what your final thoughts are about quantum materials, or maybe talk about a recent result or a material science issue that you think is really critical that you'd like to leave people with. So maybe starting with Chris.
Thanks for putting me on the spot, Rick.
Sorry, Chris.
I think this is just a really fascinating area of study. The resolution and precision. You heard John talk about pristine and perfect and single crystals. It's just a whole host of materials challenges that make the kind of renews my thoughts in terms of learning about materials in the first place. We see a lot of demonstrations now that this is not just a fad, that industry is picking up with interest, that it is completely different than computing that we have today. So I just find everything from the applications to the emergence of possible demonstrations and the science to be very rich.
Thanks, Chris. John?
So I think the most interesting thing to me, especially from a material science perspective, is that we're entering into this realm of kind of non-trivial materials engineering, where rather than looking for exotic compounds that might exhibit certain types of topologically non-trivial behavior or other sorts of non-trivial quantum behavior, we're getting to the point where the material science is good enough that we can reliably engineer the couplings to be exactly what we want. So to put pattern semiconductors, superconductors, and normal metal together such that we get this complicated fabric that exhibits this fascinating collective behavior. And that right now we have a great application for that. These Majorana fermions to do topological quantum computing. But I have to think that there are going to be other exciting topics that these techniques that we develop here are going to be useful for in the future. So I think that's pretty exciting and a whole new tool set to play around with.
Well, thanks both of you. The symposium that we're hosting will be Tuesday at the MRS meeting. It's titled Material Science to Empower Quantum Information Technologies. It starts after the plenary lecture on Tuesday morning and will continue through the afternoon. and we hope people will come and listen to the experts that are speaking there and learn something about quantum materials and maybe bring their own material science expertise to this really interesting problem. Thank you.